All right, so this week we're going to continue with algorithms and algorithm analysis. Today we're going to focus on asymptotics. Remember that we are online. We're on Piazza. If you've got any questions, go ahead and post there. Otherwise, again, remember the motivation for doing this? That we've got a 5-step process for determining, given an algorithm, how well does it perform. At the end, what we're going to do is we're going to characterize that in terms of big O analysis so that we can have one algorithm and another algorithm, and one of them is order n squared and another one is order n squared. You can come to the conclusion, well, asymptotically, they're no different. Or you can say that, well, this one is exponential and this one is polynomial. Definitely this one is better. And to do that, we need a way of characterizing functions. So again, remember our motivation. We want to characterize an algorithm's performance. And when we say performance, we mean multiple things. We can mean time, we can mean power consumption, we can mean extra memory that it needs, right? And efficiency with respect to its input size. But we're not interested on just one input or just a few inputs. We're interested in its performance as n, that is the input size, grows. Right? So we're not going to be interested in small amounts. Remember when I ran the original demo that started this all off? 10, 100, 1,000, they all ran blazingly fast. There was really no difference between the runtime on small inputs, right? We're looking for larger and larger inputs. For larger and larger inputs, how does the growth rate of the function that characterizes an algorithm's efficiency grow, right? Or look, or the growth rate of the function that characterizes the algorithm's efficiency, i.e., what kind of order can we give it, right? For small input sizes, again, the practical differences don't matter much. But in addition, we don't want to have to worry about those small order things, right? If I've got a polynomial of degree 3, and I look at as n tends towards infinity, all those lower order terms, they're not going to matter, right? It's the n cubed that's really going to matter. And also that constant out front is not doing anything. If you were to graph n cubed and n, n cubed and 50n cubed, right? It would just steepen the curve a little bit, but basically the growth rate would be matched, right? And if you're adding terms, you're basically just shifting the curve up. It has the same order of growth as n tends towards infinity. So we want to be able to ignore constants, right? We want to be able to ignore lower order terms, right? And the tool to do this is a very old tool. It's asymptotics, it's big O analysis. It's from calculus, hundreds of years ago, and it was adopted by, I believe, I can't remember his name, but it was proposed that we use that as a measure for algorithmic efficiency once we characterize the runtime of an algorithm as well. But the tool we use for this is big O analysis, right? Now there are several asymptotics and asymptotic characterizations. There's theta, there's omega, there's big O. O is, by the way, a Greek letter omicron, but there's no difference. Literally, there's no difference between the Greek letter omicron and our letter O. In fact, if you try to typeset this in LaTeX, there is no omicron. There's just big O, right? But there are also little asymptotics and stuff like that. If you're interested in that, check out the pre-prepared videos because I do cover that stuff. It requires calculus, which is why I don't cover it in the main section here. But basically, you just have to set up a ratio of f of x and g of x, and take the limit as n towards infinity, and one of three things will happen. It'll either diverge, it'll converge to 0, or it'll converge to some constant, non-zero constant. And based on those conditions, you can conclude what the asymptotics between those two functions are. Again, we're not going to go that. We're not going to do that. What we're going to do is we're going to use the definition. Right? So what does it mean to say that one function is big O of another function? So definition. Let f of n, and by the way, when I post these notes to GitHub, sadly, even after 10 years, GitHub is still not supporting LaTeX in their Markdown, and may never. But I've been furiously looking for alternatives to that. But whatever. Let f of n and g of n. You'll just have to imagine what they look like when they're typeset like this, right? Up on the screen here, they're being rendered using LaTeX. But when you see these notes on GitHub, you won't see the rendered LaTeX. So unfortunately, be functions. We say that f of n is big O, and again, omicron, but O, who cares, of g of n. And these are both functions, right? If there is a positive constant, c, and an integer, n, not such that f of n, and I will typeset this all lower, is less than or equal to c g of n for all n greater than or equal to n not. All right? So that's kind of a complicated definition, but it has an intuitive notion that intuitive interpretation that I'm going to show you here in a second. Basically, the first intuition that you should have is that f of n is g of n if g of n is growing at least as fast as f of n. That's why we use this less than or equal here. Right? The thing on the right-hand side is at least as great as the thing on the left-hand side. And big O allows you to say not just that for a particular n that this inequality holds. It means that at some point in the function's growth rate, that one function will overtake the other function and always be greater. Here's an example. 212 n squared plus 50n versus n cubed. We have an intuitive notion of which one of those functions is larger. Which one? N cubed. But if I were to map these out, or if I were to plot these out, excuse me, and I've got them done over here in Wolfram Alpha, and I only looked at small input sizes. Remember, the interpretation of this graph is that the x-axis is the input size. So I'm looking at input sizes 0 to 100. Linked lists with at most 100 nodes, if you want to think of it that way, right? And what am I mapping on the y-axis? Some resource measure, time, memory, power, whatever. And if I look at these two characterizations, then the one that is higher is using more of those resources than the one that is lower, right? And you can see here that the red one is actually lower. So if I only look at small input sizes of a linked list of 0 to 100, you would get a mischaracterization of the terms of these two functions, right? Which one is lower? N cubed. That's against the intuition that you just told me that n cubed is the larger function. Certainly it's the larger growing function. And we can see that if I zoom this out. Right? And if I look at input sizes 0 to up to 300, now I see a crossover point here. At which point the red one, which is n cubed, that starts to dominate. That, in fact, all the way to infinity, that function will be larger than the blue function. Right? So the interpretation here is that if these are two algorithms, and these are two functions characterizing the performance of two algorithms, you would, and you only looked at input sizes 0 up to about 250, you would get the mischaracterization that the n cubed is somehow more efficient. The only reason that you would get that mischaracterization is that we've got these constants sitting out front. We want to get rid of that mischaracterization by getting rid of those constants. What we want to do is we want to get to this point and say, okay, well, after this point, input sizes of greater than 300, then clearly this one is the better algorithm, and it will be better for all input sizes off to infinity, right? That's what we want, and that's the interpretation of this definition right here. Let's read it again. F and g are two functions. We say that f of n is big O of g of n. In other words, f of n is you can say smaller, but not strictly because of the less than or equal to. So it's more accurate to say that g of n is at least as big as f of n asymptotically if there is a positive constant c and an integer n such that after a certain point, for all n greater than n naught, that this inequality will hold, right? In other words, after this point, there's my n naught. Right? What I need to do now is start formulating ways to go about proving these things mathematically. Okay. So again, to summarize what we just said, big O characterizes the function's order of growth as n tends towards infinity. Again, that's a little bit calculus-y. Don't worry about it. We're not going to use calculus here. We're just going to use the definition. And it achieves exactly what we wanted. It allows us to ignore lower order terms because at some point, only the largest order term in that sequence is going to dominate. It allows you to ignore constants because of that c sitting out front. Right? You can fold all the constants into that c and be done with them. It allows you to focus on the most significant term in a function, basically. Didn't copy that over. Sorry. There we go. All right. So here's some miscellaneous, I guess. We usually write f of n is equal to big O of g of n. This is technically incorrect, right? We usually write it like this, but that's only because we assume no background in discrete mathematics. If you're taking 235, the real way to write this is, of course, using set notation, because big O of g of n is a class of functions. It's a whole set of all the functions that have that order of growth. And so we should say that f of n is a member of that class of functions. Again, don't worry about it. This is kind of an abusive notation, but it's so common that everybody gets away with it, right? All right, so it is also note that the definition is not tight, in that it only establishes a relative order of growth between two functions. It does not say that these two functions have the same order of growth. Remember, we're using this less than or equal to. It could be that one function's growth rate is strictly greater than the other function's growth rate. It could be that the growth rate of these two functions is equal, in which case we have different asymptotics. That's little o notation and theta notation. But we're not going to cover that in this class. Usually that's covered in, say, 235 or something like that. But here's some examples to illustrate what I mean. If I have a function like this, characterize that function. 3n plus 3. That's a linear function, right? So I would write that its order of n. I would simplify it as much as possible. But it's also true that 3n plus 3 is order n squared. There we go. Right? The thing on the right-hand side, the order, can be bigger. Right? It can be bigger, and you can keep going. Right? You can also say that it's bounded by an exponential. It's also true that this is going to be, if I'll just switch these around here, that it's exponential. Right? Again, it only establishes a loose bound, that this thing is at least as big as this thing over here. If you want exactitude, if you want an exact characterization, you're talking about big theta notation. And big theta notation means that you have to bound it from below and above to trap this function, right? And we're not going to do that. We're just going to stick with big O notation, okay? So let's talk about how we go about proving these things. So proofs. Given two functions, again, f of n, and we're just making them generic here, f of n and g of n, right? How do you prove that f of n is big O of g of n? Right? There we go. And you can, of course, use calculus. In fact, in my opinion, calculus is the most simple because all you have to do is set up a ratio and take the limit method, and now you've got this entire calculus toolbox of things that you can use. L'Hopital's law, first derivatives, second derivatives, etc., right? And a whole bunch of other things that you can immediately bring to bear on that proof, but we're not going to go there because we don't assume calculus. But we do have just two algebraic techniques that don't rely on any calculus. So here are the two techniques that I'm going to show you. Approach A. This is the less useful approach. That's why I'm going to do it first, and then I'll show you approach B. Find the crossover point where one function will become larger for all values larger than that crossover point. In other words, going back to this visualization over here, find this point, at which point you can say that this function is always going to be larger than this function. Right? They might cross over like multiple times. If you've got really complicated polynomials, right? You've got it moving all over the place. And they might cross over 6 or 7 times if you've got very high degree polynomials. We're not going to do that by hand. We wouldn't do that to you. If you did have to do something by hand like that, then use a tool like I'm using here, Wolfram Alpha. But otherwise, the idea is find this crossover point. That is equivalent to, it is essentially fixing C to be 1 in the inequality and finding N naught. Because remember, the definition has these two numbers that you have to find. F of n, g of n are two functions such that there is a positive constant c and an integer n naught such that this inequality holds for all n greater than or equal to n naught. All I'm doing is getting rid of one of those things in the equation. I'm just getting rid of c here. And if I get rid of c by making it 1, then all I have to do is show that f of n is less than or equal to g of n for all n greater than or equal to some crossover point like this. Right? That one's pretty easy. All right? In fact, let's go ahead and do it on that example that we just did, that I just gave. Sorry. Unlocking. Maybe I should take a picture of my face with my iPad with my mask on, because it will not do face recognition. I have to give it the pin every single damn time. All right, so here we are. We've got those two polynomials here, right? So what I want to do is I want to fix c to be 1 and find n naught such that 212 n cubed plus 50n is less than or equal to n cubed, right? This is f and this is g. Right? And remember that I've got this 1 sitting right here. But I've gotten rid of it I've got the c sitting right here, but I've gotten rid of it by making it 1. And so we can go ahead and effectively get rid of it from the equation entirely. For all n greater than or equal to n naught. I need to find this n naught right here. Okay? That should be pretty easy. All I have to do is solve for n, right? So let me go, how do we solve for this? This is an inequality, first of all. With inequalities, I can do any algebraic tricks that you can pull out with an equality. In other words, what happens when these two functions are equal? In other words, graphically, what happens when these two functions intersect? Okay? So what I'm going to do is I'm going to change this so that it's an equality, because that's what I'm looking for. Go back. Sorry. 212 n cubed plus 50n is equal to n cubed. For n being what? Right? So what I'm going to do is I'm going to rewrite this so that it's more obvious on what I'm looking for. N cubed, I'm just going to take all of this stuff and move it over to the other side. That's minus 212 n cubed minus 50n is equal to 0. Now does it look familiar? You want to find out what n's give me this equation. In other words, you want to find roots. Now this is a cubic equation. So does anybody know how to find roots of a cubic equation off the top of their head? No. It's an exercise that's probably shown in algebra classes once to tell you that, well, there are a couple of cases here, and then you basically reduce it down to an n squared, or a quadratic equation. Now do you know how to find roots of a quadratic equation? The quadratic formula. And that's why I wrote it like this without a lowest order term, so that we can immediately factor out an n here. Right? Here's one root when n is 0. Right? By factoring out an n to all the, right, because if I take n being 0 here, 0 here, 0 here, I certainly get 0 when I add up 3 zeros. Right? So I concocted this so that we could do this trick. Right? Once I've taken out an n, then that reduces this down to n squared minus 212n minus 50 equals n. Right? Now, do you know how to find the roots of that thing? Certainly. b plus minus square root b squared minus 4ac all over 2a. Right? Now we can go ahead and do all the algebra if you really want to. What was b again? Negative 212, right? Oh, sorry, negative b. So 212 plus minus 212 squared minus 4a. A is, in this case, is 0. C is negative 50. So plus 4 times 50, right? All over 2a, and a is 1. Right? Plug that into your calculator and tell me what you get, or I'll plug it into Wolfram Alpha for you. What are the roots of, and I'm just going to grab this other, here, I guess, n cubed, what was it? Minus 212n squared minus 50n equals, and I don't think you need equals 0 here on Wolfram Alpha. It's pretty smart about figuring out what you want, and we get those 3 roots. One of those was the predictable root at 0. What's the interpretation at 0? Well, certainly for an input size of 0, it doesn't matter what the algorithm does. It doesn't do anything, right? So both of them take 0 time to execute, 0 memory, 0 power. Don't even run it, right, on an empty input. What about this input right here? It might be kind of hard to see, but I'm going to open it up and look at the actual numerical value here. It's negative. What's the interpretation on that? There isn't one because, I mean, mathematically there is, because these are just functions. But what are we doing? Again, n is an input size. Can you have a negatively sized input? Nope. So forget about that one. This is the one that we care about. 212, or I estimated about 250, right? 212.235, blah, 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 blah. Do we need to worry about blah, 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 blah? Remember, input sizes, right? Can you have a linked list with 5.5 nodes or 212.23 nodes? No. So let's go one more. 213, right? So for n naught being, and I just did this, by pulling out my calculator and eliminating them all. For 213, the inequality holds. I couldn't have gone with 212. Why? Because it's not true. It only 212.23 is the actual crossover point. I just needed to go one more, right? So, oops, sorry. So I needed 213, right? You need integer values here. So for n naught, the inequality holds. That what were they again? 212 n squared plus 50n is less than or equal to c being 1, right? Just remind ourselves of that. N cubed for all n greater than or equal to 213. And there is my proof, right? Now, if I didn't give you a nice polynomial like that, where I can easily factor out one of those factors, guess what? I gave you a degree 8 polynomial and another degree 9 polynomial. Didn't remember how to do roots of a degree 3 polynomial. Are you going to remember how to do roots of a degree 18 polynomial? No. Screw that. All right. So here's approach B. Approach OBS is not connected. Where did we lose it? Oh, it is. Okay. Never mind. It's just getting choppy. Hopefully the full thing is fine. But anyway, approach B. We fix n naught to be, say, 0, and then find a C such that the inequality holds. Right? So approach B is, we've got two variables here, right, that will contribute to showing you the proof. Fix one, find the other. Fix the other, find the first, right? And so for this one, I'm just going to simply say, all right, let those be functions here. What I'm going to do is I'm going to make C bigger and bigger and bigger and bigger and bigger. What does that do to a function, right? So let me go ahead and come back over here, and let's get rid of the plot of one of these things. Right? All right? Plot that. Right? That looks like that. If I add a term, if I multiply this by a constant, say twice as big, is it going to change the overall? What's it going to do to this parabola? Is it going to change the growth rate of this thing? No, the first derivative is still the same order, right? But what's going to happen if I double it? What's going to happen to the parabola? It's going to stretch it, or like this way, right? And I don't know if you'll be able to see that with the graphs on this thing, but yeah, it's just going to change the scale on the x and y axis. It's just going to draw it the same here, right? But am I changing the order of growth if I make it bigger and bigger and bigger? No. So I can take the same approach over here with these functions. In other words, I will, let me write this out, start with f of n and make it bigger and bigger until you get g of n, right? And that gives you a C for which it holds. Sometimes you also have to increase the n naught, and that's fine too. But you start at n naught being 0. Okay. So let's see what that kind of proof looks like. All right, and let's go over here. So I'm going. Come on, not now. Yes, I am enjoying good notes. All right. So what was it? 212. Oops. 212 n squared plus 50n. Basically, what I know, 50n, excuse me. What I need to do is I need to show that this is less than or equal to c g of n for all n naught, n greater than or equal to n naught. Okay. Sorry. There we go. So I need to find a c that is less than n cubed. Or I need to find a c such that this inequality holds. Okay? We need to show this. To find a c such that we've got this. Okay? So let's start out with the left-hand side. 212n squared plus 50n is less than or equal to something. Now I could get crazy, and I could make this super, super big. 1 million n to the 15th, right? That's pretty obvious. But what have I done? I've overrun the thing that I'm trying to show here. I'm trying to show this for n cubed. Right? I don't want to make it look just big. I want to make it look like something like this. Okay? So how do I do that? Well, oh, I could multiply the whole thing by n, right? So I could say that this is less than or equal to n times 212 n squared plus 50n, right? That's certainly true for all n. For all non-negative, it works for 0 too, right? For all n greater than or equal to 0, right? Okay, well, now that thing on the right-hand side is equal to 212 n cubed plus 50n squared. Right? Okay. Now I can multiply the whole thing, but I can also add. I can multiply individual, terms, et cetera, et cetera. What if instead of multiplying the entire thing by n again, because that would get me up to n to the fourth, which is too big, what if I just multiplied the second term by n? Is it true that 212 n cubed, or that this thing right here, is less than or equal to this thing right here? Oops, sorry. Yeah. Again, for what? For all n greater than or equal to 0. Right? You're just making one of the terms bigger, and if you make one of the terms bigger, then the entire thing becomes bigger. Right? Wow, I think we're there. What's that equal to? 262 n cubed. Right? So, for n naught being 0, and c being 262, the inequality holds. Right? Now, that's much bigger than what we came up with approach A. 213, if you remember. Does it matter? No. Bigger, 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 who cares? Remember that this constant term is ultimately ignored. So the conclusion in either case is that 212 n squared plus 50n is big O of n cubed. Okay? Now, that didn't take too long to present. So, but as with everything new, practice makes perfect. If you will, hopefully you've been looking forward to assignment 8. Assignment 8 is something that we usually require, and we grade at the end of the semester. But because of the 14-week schedule, as well as the accommodations for, I think it's wellness accommodations, right? We made this required but not graded. And a couple of people have already asked what that means. What that means is that you should do it, right? We're not going to police you to say that if you don't do it, oh, that's bad, right? It just means that if you go on in the program, you're going to be expected to know this stuff, right? And that means having watched the pre-prepared videos, engaged in this lecture, read the book, right? We're on chapter 4 or 5 right now, right? I go through this as well as multiple examples. And this is the homework that you would normally have. Since we're not grading it, let's do it, right? So 3n versus order n. Guess what? 3n, we start you out easy here. We want to prove this. Right? Let's go with approach B. Right? In fact, let's think about the graph here really quick. What does it look like? There's the graph of n. What does 3n look like? Slightly steeper, right? But the order of growth is what? The same. The first derivative is a constant in one and a constant in the other, right? These are clearly equivalent asymptotically. And it was also designed to be super easy, right? 3n is less than or equal to some cn. Give me that c. Oh, okay, 4. I was going to go with 3. I was going to make it a little bit tighter. For c equals 3 and n not being greater than or equal to 0, n being 0, the inequality holds. Right? If we were doing the limit method and we had, say, the limit as n tends towards infinity of 1 over n. This is not having to do with 3n right here. But if we had this, I would characterize this as being an obvious land. What is the limit of a monotone growing function in the denominator? The bottom is getting bigger and bigger and bigger, so the entire thing is getting smaller and smaller and smaller until it reaches 0, right? It never actually reaches 0. It's in the limit, right? But here you are in obvious land, and you can say that this is equal to 0. Right? It does not require a proof. When you transport that thinking over here to the algebra world, this is almost obvious land, right? Once you've identified these two numbers, the rest of the proof is obvious and straightforward. Right? All right? Let me go ahead and move this over here so we can see these functions. All right, 500n squared is big O of n. Remember, it doesn't have to be tight, right? I could say that 500 square root of n is big O of square root of n, right? Because square root of n is a polynomial with exponent what? 0.5, right, or 1/2. Right? So let's go ahead and prove this. 500 square root of n is less than or equal to some c of n. Right? Again, you're kind of in obvious land here. What could you say immediately? We want to show this inequality. That's what we want to show eventually. So let's go ahead and show the actual process here. 500n, that's certainly true for all n greater than or equal to 0. Does it work for negative values? Okay. Yeah, imaginary numbers, right? If I had negative values, this doesn't even make sense anymore. Thankfully, we're computer scientists, and we don't have to worry about that. Negatively sized input, that doesn't make sense. We throw that out. An input size of 3.5 doesn't make sense. We throw that out. Right? Most of our functions are well behaved. Of course, you can start talking about weird functions like, say, sine of x versus n. What? So what does that look like? What does sine of x look like? This thing. Right? That can characterize the behavior of an algorithm, but guess what? You just have to bound it from below and above. And is it growing at all? No. Right? So it's effectively 0. You can have order 1. Right? But this doesn't really make sense, right, to compare these kind of functions. In general, again, if you want the math side of this, we're only concerned with monotone growing functions. We're not concerned with weird functions like sine that oscillate. Okay? You can have constant functions. Right? You can have linear functions. Right? You can have quadratic. Right? Or you can go ahead and just take any n to the k, and that's polynomial. Right? What's bigger than polynomial? Exponential, okay. So order 2 to the n. Are all exponentials created equal? That's the next. That's one of the next questions. Right? Mike Trout is definitely the best player ever, but he's not my favorite player. Right? But thank you for the notice. Right? This is exponential. Order. Oops, sorry. 3 to the n. Are those two exponentials created equal? Nope. Right? And if you take the first derivative, it tells you that they're not equal. Right? But if you take the limit, it tells you that they're not equal. Right? But again, we're not looking at inequality. We're just looking at setting up a relative order of growth. Right? You can have super exponential. What is that thing? That's an exclamation point, by the way. That's factorial, right? This is super exponential. You can also mix in logs. For example, order n log n. That's a lot of sorting algorithms. Quick sort and merge sort, which we may review. Where does it fit in with all of these over here? Well, it's bigger than a constant, right? Because it's monotone and growing. Is it bigger than linear? Yeah, because we've got this other log term here. But is it bigger than quadratic? Nope, because log and n, they're not equal. N is greater than a logarithm. So if I just had a logarithm, it would be couched right here. Right? Logarithmic. Right? Kind of like a binary search. Remember that? Right? N log n would fall right in here. In fact, there's a name for this. We call this quasi polynomial because it's almost polynomial. And there's yet another asymptotic that you can use, order with a tilde above it that basically allows you to throw away not only constant terms, but also logarithmic terms, because logs are such slow-growing functions. Who cares, right? But I'm not going to cover that, right? Let's do another example. What about this one? N squared plus 2n plus 1 less than or equal to c of n squared. Again, you just have to show an inequality. Start with the left-hand side and make it bigger. I could replace this term with 2n squared. I could replace this term with n squared, certainly, right? So n squared plus 2n squared plus n squared. I just made this term slightly bigger. I made this term even more bigger, right? And so I come up with, this is for all n greater than or equal to 0, of course, because if you're at negative values, nope, that doesn't necessarily hold. And so now I can collapse all these into 4n squared. Right? So for n naught being 0 and c being 4, the inequality holds. Let's see if we can do something a little bit more complicated. What about e? Oops, and I've run out of pages. All right, e is going to be n log n, or log of 32n, and n log n versus, all right? Again, this is intuition time. In order to show the proof, you have to have an intuitive knowledge of which one is larger. So which one of these things is larger, would you say? Left-hand side or right-hand side? Left-hand side? Okay. So we want to show that f of n is big O of g of n. In other words, we want to show that n log n is big O of n log 32n. All right? In other words, we want to show that n log n is less than or equal to some constant times n log 32n. Okay? So let's set up an inequality. N log n is less than or equal to, how do I make that bigger so that it looks exactly like this thing right here? Well, it already does, right? C n log 32n, right? This 32 right here, it's positive. Positive of a monotone increasing function, positive input of a monotone increasing function is still monotone increasing. So for c being 1 and n not being, careful, 0? Just like negative values are not defined for a square root, 1, why wouldn't 0 work? Log of 0 is what? It would be, what, negative infinity? Something like that. What about log of 1? That would work, right? It'd be 0, right? And 0, and the left-hand side would end up being 0. The right-hand side would end up being bigger. It'd be log of 32. Log of 32 is 6. Right? Remember, all of our logs are in base 2. Okay, so for n being 1, oops, that value holds. Okay? But let's try to show the other way. Right? These are actually equal. Right? You could say that one is big O of the other and vice versa. Let's go, what we wanted to show over here was that this thing, or that n log n is bigger. Right? That's what we wanted to show in the actual homework here. So let's go ahead and do that now. Right? We want to show that n log 32n is less than or equal to some c n n log n. Can we show that? That's going to take a little bit more algebra than this trivial proof up here. So that's a little bit more, not that much more involved, but let's go ahead and see what it looks like. N log 32n. Remember your log identities. What happens when you've got log of a, b? Log a plus log b. Good. Something like that. So 32 times n can be expanded out. N times log, and I'm going to switch them around. I'm going to put the second one first, plus log of 32. Okay? What is log of 32? That's a constant, 6. So this is n log n plus 6. Right? Or 6n, sorry. Don't lose your n. It was sitting out front here. And I distribute it, and I've gotten this now. Well, now we can use our old trick. By the way, there's no inequality here at all. This is just all equalities so far. So, dot, dot, dot. Let's go to the next page. And again, what we've shown is that n log n, sorry, I don't know if I can, yeah. N log n plus 6n is less than or equal to what? We want to make it look like this thing right here, c n log n, with some c sitting out front. So we can make it bigger. We can make the second term here bigger by making it into, don't lose the first term, but by making it into 6n log n. Right? And that's certainly true for all n greater than or equal to 1, right? So this is equal to 7n log n. So for c being 7 and n not being 1, the inequality holds. These are just some same variations, and that's why I always hesitate to give you so many on a homework, because once you get into the groove, the rest of it is kind of busy work. I do like G though, or at G and H. Let's do G and H. Okay, so I want to show on G, I want to show that n 2 to the n is bounded above by 3 to the n. Right? I want to show that n 2 to the n is less than or equal to some constant c to the n for all n greater than or equal to n naught. Right? And for n naught, I'll just make that equal to 0 for now. Okay. So let's start out by going like this. Now, what I could do, and this is usually the first step people try, is I want to make it into an exponential. I want to get rid of that n term out front. So I could say that this is less than or equal to 2 to the n times 2 to the n, right? Certainly it's true that n is less than or equal to 2 to the n, but for all n greater than or equal to what, though? N is less than 2 to the n for all n equals 0? That works. N equals 1? That works. 2? Yeah, that works. So I'm convinced that it works for all n. But this thing on the right-hand side is now what? Well, oh, not 4 to the n, but it's 2, it's 2 to, yeah, 2 to the 2n like this. There we go. Right? Because it's 2 to the n plus n. Excuse me, n. There we go. Right? But now simplify that. Now it's going to be 4n. But guess what? I've overjumped my bound that I wanted. All right, let's undo. And man, I wish I had this kind of technology when I was doing math, because of course you fill up paper after paper. Oh, that proof didn't work. cross it all out or just throw out paper away. You can't just go back, okay, I made my mistake right here. All I have to do is erase up to that point. And also, once I've got it written out on an iPad here, I can go ahead and dump it to a PDF and print that and hand that in. Wonderful, right? No, instead I had to type out LaTeX. All right, so help me out here. Same algebraic trick. Right? If I did 2 to the n, 2 to the n, right? Ultimately I combined these and made them 4 to the n. Right? How can I combine them to make them into 3 to the n? In other words, don't make that one so big. What here will give me 3 to the n? 1.5. And 1.5 to the 0, that inequality holds, right? Just do the same thing over here. N is less than or equal to 1.5 to the n for n being 0. Yep. For n being 1. Yep. For n being 2, I don't know. Pull out your calculators. What is 1.5 to the second? Oh, 2.25. Okay, we're safe still. What is 1.25 to the third? Okay, it's still greater than 3. I'm convinced. Right? I'm convinced that we're in obvious land here, that 1.5 to the n is greater than or equal to n for all n greater than or equal to 0. Right? So that gives me 3 to the n. So for c being 1 and n being and not being 0, the inequality holds. Right? You just have to come up with some decent algebra to do stuff like that. Right? And by the way, for all of these things, there are an infinite number of combinations of c and n naught, if it's true. Right? If it's true, you can come up with just change your c, that gives you a different n naught. Right? In fact, for a particular c, you've got an infinite number of n naughts to choose from because it's a growing function, because you're never going to run out by going along the x-axis. Maybe one more. Where's my homework? There we go. So log of a factorial. A factorial is huge. It's super exponential versus n log n. Right? But a logarithm of a super huge thing becomes more manageable. Right? So what's your intuition? What about these two things? Which one is bigger? Just from, oh, well, n factorial, that's huge. That must be bigger. We can go with that. So our first attempt here is to show that n log n is big O of log of n factorial. There we go. So let's set up our inequality. How do I make it look like n factorial? I could make it look like n log n factorial. That's certainly true, right? Because all I'm doing is taking n and making it bigger by making it n factorial. But is that what I have over here? Nope, I've got this thing right here and I need to make that disappear. Right? Can I make it into a constant? Nope. Because n is what I'm trying to show this for. Right? That's my x on my x-axis. Oh, okay. Let's back up. I could move it into the logarithm. That's interesting. So again, what are your log identities? Log of x to the n. Actually, log of a to the b is equal to what? B log a. Doesn't matter what a and b are. And you can work in reverse. So this is equal to log of n to the n. N to the n versus n factorial. It's bigger, and so it's too big, right? That n to the n is actually strictly greater than n factorial. Why? What is the definition of n factorial? N times n minus 1 times n minus 2 times ... 2 times 1. Right? I can make that bigger by changing all of them into n, right? Because certainly n minus 1 is less than or equal to n minus 2 is less than or equal to n ... 2 is less than or equal to n, 1 is less than or equal to n, for all n greater than or equal to 1, right? And that is equal to, how many n's are there here? N of them. So n times n times n times n times is n to the n. So what we ended up doing here is we actually ended up showing the other way. We ended up showing that, let's see, n log n, or the other way. Come on. Actually, what did we end? Yeah, we ended up showing that log n, which is actually what's in the homework, is big O of log of n factorial. And again, let's go over it. Sorry. Oh yeah, that's still backwards. Sorry. Log of n factorial is big O of n log n. That's what's in the homework. I'm looking right in front of me right here. That's what's in the homework. And how did we end up showing that? Well, log of n factorial is equal to log of n times n minus 1 times n minus 2 times ... 2 times 1. Now apply the same log identity. I mean, you could do the inequality first, or you could apply a log identity n times, and I'll go ahead and say that I'll go ahead and apply the inequality first. This is less than or equal to log of n times n times ... n times n, which is equal to log of n to the n, which again, now I'll apply the logarithmic identity and take that n out front. Right? So for c being 1 and n not being, you do have to be careful there. Oops, nope, that's not what I wanted. Sorry, there we go. N not being, well, 0. Nope, log of 0 is undefined, so we have to jump up to 1. Actually, log of 0 is undefined, but what is 0 factorial? It's 1. Why? Okay, it works out in some maybe Taylor series or something like that, whatever that is.
1 factorial equals 2 factorial over 2. So 1 factorial is 1. And so 0 factorial is 1 factorial over.
Okay, so coming up with some sort of identity. Combinatorially, though, what is a factorial capturing the idea of? If I've got 4 things here, right, 4 distinct things, A, B, C, D, it's arrangements. I could go let's go 3. A, B, C. I could go A, C, B. Here, I've got something to write on. A, B, C. Let's just go with A, B, C. A, C, B. What's another way I could write it? B, A, C. B, C, A. Then I could start with C and go A, B. Or I could go C, B, A, right? These are called what? Permutations. Right? And the number of permutations of n things is going to be n squared. Well, what if you only had one thing? How many permutations are there of A? 1, right? That's why 1 factorial is equal to 1. You just put it there, and that's the arrangement. What if you had nothing? Right? What if n were 0? What is n factorial now? How many ways are there that you can arrange nothing? Mathematically, it's got to be one. You don't do anything, right? That's got to work out that way, right? And so how many ways are there of arranging nothing? One. You don't do anything, right? You do have to count that. All right. But by the way, you can also show the other way. It's just, it requires, it might require like Stirling's formula or something like that, where you characterize n factorial in terms of this continuous function that involves n to the n, and another 2 to the n and a square root and a bunch of other stuff. Forget about it. Okay. All right. Questions so far? No? That was all our homework there. So if you're watching lecture, you did your homework for the most part, at least part of it. All right. Dot, dot, dot. There we go. So we already looked at insertion, selection sort and insertion sort. We analyzed those, right? What about other sorting algorithms that we may or may not remember, right? Or other algorithms that we may or may not remember. Remember binary search. Actually, you probably also remember linear search. Do we even need to look at linear search? What's its order? Order n. Why? Because you go through everything making at most n comparisons, and then you're done, right? So we will look at binary search again. We'll also look at quicksort, and we'll look at merge sort, which you may or may not have seen, okay? With the rest of our time today, I just want to give you an impression of how each one of these things works, okay? An intuitive notion of how they work so that we can actually work off of them when we come back next time, right? So binary search, 2, 7, 8, 4, 28, 72, 101. There we go. Why did I write that in order? Remember how binary search works? It divides it into 2, right? In fact, it jumps to the middle here, middle. And I'm searching for, let's say, 2, right? Just as an example here. I jump into the middle, and I see 14. Well, if I know that it's sorted, how can I exploit that? I know that, well, it's not equal there. So do I even need to bother about everything over here? Nope. All I need to do is recurse or reiterate on a list that's half the size. Again, if you want to look at this more generally, you are searching, search for k in a sorted array. Right. And now why am I being more specific here with an array? Ultimately, what I'm going to do is I'm going to be jumping to the middle. Can you do that with a linked list? Can you jump to any location in a sorted linked list? Nope, you have to start at the head, go next, next, next. Okay, now I'm at the middle, right? And okay, I need to go this side or this side. Can you do that? You can't do something like that with a linked list. I mean, you can do it, but you lose your efficiency. You can't immediately jump to this middle location. You're ending up doing a linear amount of work even to just get to the middle. So that's why I'm being more specific here about an array. It only works if you have random access. You search for k in a sorted array. In other words, you have this array here, and you jump to the middle. M. Right? One of 3 things is going to happen. If the value stored at m is equal to the key k, you stop. Output k, or m. That index at which you found it. You got lucky. You jumped to the middle and you found the element. And if that was sorted, by the way, you just found also the median element. Yay. Else if, the thing that you're looking for is less than a sub m, else if the thing that you're looking for is greater than a sub m. Those are the only three possibilities. So if it's less than a to the m, where do you go? You just go to the left-hand partition. I'm going to give these left and right. Right? So search the left part. And and if it's and if the thing that you're searching for, k, is greater than this element right here, a sub m, then you need to go to the right. So search the right part. Okay? That immediately jumps out to me that we can do a recursive solution. Right? Now, I know in CS1, and we kind of skipped recursion, or at least the lab on recursion, which would have been in week 12. The lab in both the hack in computer science 1, if you took it from me, or this lab are designed specifically to show you why recursion is bad. Because you end up doing for the most part, doing a lot of additional recursive calls when you don't need to. It's very, very inefficient, even if you don't end up doing redundant recursive calls, etc. And there are much better solutions. Right? You can always simulate recursion with a stack. You can always simulate recursion with a regular old loop rather than abusing your call stack to simulate your loop. But in any case, let's go ahead and actually look at the recursive version of this algorithm. Right? So here's binary search. What I'm going to do is I'm going to write a recursive version of binary search that takes as input an array, a key, k, and indices, L and R. Right? Because what we're going to want to do is we're going to want to keep track of L and R. Initially, L is going to start at 1, and R is going to start at n, however many things are in there, so that we can compute m here. Okay? Our stopping condition, and we're going to output the index unindex such that a sub I is equal to the key k, an index I. Right. So binary search takes A, the key, L, and R. Okay. I do need a stopping condition here. So left and right are going to be updated. Initially it's 1 and n. I jumped to the middle and I said, oh, I need to go onto that side, the left side. That updates my right. Then left gets updated. Right, left, right, left, right. When do I stop and say it's not in there? Well, if they're equal, if left is equal to right, then what? I still need to search that element. Is that the element I'm looking for? But if once these have jumped past each other, guess what? Unsuccessful search. Right? So if R is greater than L, then output phi, no such element, just like we might have done in a linear search. Else, actually, let's compute that middle element here. M is going to be what? I want that index. I want the index of the middle element given L and R. All right. Initially, it's a 1 and n, but in general, it's L and R. How do I get to the middle element given those two values? Think about this as on a number line. If I've got integers, L and R, sitting on a number line, I want the one right in the middle. I want their median in this case of that range would be the same thing, but how do I compute it? R minus L will give me the range. Divided by 2 would give me this quantity, not this point. So what I want is their average, right? Now, if you're doing this in a computer, never ever do this. This is susceptible to overflow, right? But we're doing this in pseudocode. So we're in the magic land of math where there is no overflow. If a sub m is equal to rk, output m. Else if the thing that we're searching for, k, is less than a sub m, recurse on binary search, and I'll just go ahead, binary search, on a and k are unchanged. A and k are our array and our key that we're searching for. But L and R may need to be updated now. Again, if the thing that I'm searching for is less, I need to go to the left. I need to go to the left part. So does L change? Nope. We update right R to be what? Well, remember, we could do M, but we already looked at it, right? We looked at it right here. And it's not within the thing that we were looking for. So let's go with M minus 1. Else if, and the if here is not necessary, but I'm doing it for demonstration purposes. There's only 3 cases. The else here, you could just make this into an else. I do binary search on A, K, and now here R stays the same. Right? Remember that now we're searching on this half of the list. So L will be updated to M plus 1 because we don't need to search M again. Right? There. That's good pseudocode. Now if you go through your 5-step process, what happens? The input is, of course, 1. The input, the most relevant input here, there are 4 of them. Let's simplify. What's the most relevant? 1, 2, 3, 4. Is it the key? Probably not. Is it these indices, which are just one thing? It's the size of the list here, right? Or it's the array. The size is the size of A. Right? What's our elementary operation? Oh, okay, you want to do a function call. All right. And that'll end up being exactly the same as what I'm going to do. I'm doing comparisons, right? This base case up here, that's necessary to the control structure of the algorithm. We ignore it. Otherwise, I do an addition and I do a division here. Those would be reasonable too. Right? But also, I'm doing an equality here. Am I actually doing 3? Remember that this doesn't actually need to be an else if. You could just have this as an else because there's no other case. So I'm actually only doing 2. But am I actually doing 2 here? Oh, well, if you want to think about it as doing 2, fine, go ahead. I want to simplify that and say that I'm going to collapse all 3 of these down into a comparator function call. Right? Because that's what you're going to do in practice. So what's my elementary operation? Is going to be the comparison. Now here's the problem. It's not we've used recursion. It's not a straightforward loop, right? I can't just set this up as a for loop. Oh, and it runs n iterations. It's clearly linear, right? Instead, what I need to do is I need to set up a recurrence because this is a recursion. Right? I will preview that now. What I'm going to do is I'm going to set up a function to capture how many the number of comparisons by binary search on an array of size n. And then I'm going to set up a recursion for it. Now, why did I write it out like that? C sub n is equal to C of n divided by 2 plus 1. We're running out of time here, so I'll just ask you really quickly, what is this plus 1 here? That's the non-recursive cost. I'm doing one comparison right here. Right? What about this thing right here? Like you pointed out, I am making a recursive call, but I am doing so on an input that is half the size. Right? So what we need now is a tool to, undo that. We need a tool to solve this thing, and that's what we'll cover on Thursday. Okay. No questions online. All right. How many people online? Oh, 83 playbacks. Wow, awesome. All right, have a good day.